Okay, so we're going to start talking about Chapter 9 today. Chapter 9 is about chemical bonding. And we've talked about bonding sort of just as we've gone along, particularly the ionic bond. We've talked about that prior to this. But we're going to get into the basic concepts of what makes a chemical bond. Okay? And then, in the next chapter, we're going to talk about one of the fundamental questions in chemistry. What shape is it? Okay? So first we're going to find out what a bond is, then we're going to use that information to help determine a shape. So what is a bond? It is a stable arrangement of atoms within a compound. So it's a bunch of atoms that are put together. Now how is that different than, bless you, how is that different than just say some atomic gas? Okay? The difference is these are going to be atoms that are held together. Now they could be atoms of the same type, okay? Such as hydrogen, H2, or nitrogen, N2, oxygen, O2. Remember the 7 diatomics? But what it is they're mashed together. But it's a stable arrangement, a stable mashing of the atoms together. So we've got different types of bonding. There's the ionic bond, which we've talked about. Okay? Then there's the covalent bond. This is what we see in molecules. Okay? So the ionic bond, whenever we were dealing with metals and nonmetals or metals and polyatomic ions, the main thing we were dealing with there was the ionic bond. Ion to ion. Covalent is atom to atom. Typically we see covalent molecules or covalent compounds coming from nonmetal to nonmetal interactions. Okay? But the covalent type of interaction can be of several different types. It can be polar, nonpolar, or a network of covalent bonds. Okay, we'll talk about each of those in turn. And then we also have metallic bonding. That's the last one. Metallic bonding is actually probably pretty easy to understand because what it does is it tells us, well, why are metals behaving like metals? If we have aluminum and it's just a bar of aluminum, something has to hold those aluminum atoms in place, right? In an aluminum can, something has to be holding those aluminum atoms together. And that is what we call the metallic bond. Okay? Now, all of this stuff is going to be governed by the valence electrons. Okay? The valence electrons are the important part because remember that is the outermost electrons in the atom. The electrons in the highest principal quantum number. All of those atoms all of those electrons in the highest principal quantum number. Okay? All of them. Not just one of them. Okay? We saw that when we did the worksheet on Tuesday, right? We saw how to do valence electrons. All right, was it Tuesday or the one prior to that? I think it might have been the one prior to that. Okay? So, all governed by valence electrons. Now, I kind of like to point out this dude. This is August Kekule. And Kekule is famous for coming up with the structure of benzene, which we see here. Okay? And when we start talking about that, I'm going to give you a little story about Kekule. Turns out he was like a morphine fiend. So, kind of interesting story there. Anyway. So, in order to start talking about bonding, I want to be able to talk about the electrons. And I want to do such in a shorthand. And that is what the Lewis diagram does. The Lewis dot diagram tells us where the valence electrons are. And to do the Lewis dot structure or the Lewis dot diagram for atoms is incredibly simple. Okay? You take the element symbol, so something like hydrogen, and then you add dots surrounding it to represent the electrons. So, how many valence electrons does hydrogen have? One. It's only got one. So I put a dot there. There's the Lewis dot symbol for hydrogen. Now, let's do maybe something like boron. How many valence electrons on boron? How many? 3 valence electrons. Remember, how can we tell the number of valence electrons? The group number, using A. Not the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's not 13 valence electrons. That's why I don't like that straight numbering system. I like the A's and the B's. Because 3A tells you there are 3 valence electrons. So I have to obey Hund's rule when I do this. Okay, you guys remember Hund's rule? What is Hund's rule? Not that all electrons go to the bottom level. What you're thinking of is probably the alpha principle, meaning they fill from the lowest energy up to the highest energy.
Isn't that the one for maximizing spins?
Right, maximize spin before pairing. Okay? Now, the way we show that we maximize spin before pairing on a Lewis dot diagram is we put all of our dots around the sides, the top, and the bottom before we come around and start pairing them up. So carbon, which has got 4 valence electrons, would have 4 around there, like that. Okay? What about nitrogen then? Nitrogen has how many valence electrons? 5. So I would half fill all those spots. Now that I've gone all the way around nitrogen, now I can add a pair. So put a pair there. Okay? Does that make sense?
Yeah.
The reason we do this is this tells us the number of bonds that these atoms are going to form. Hydrogen is only going to form 1 bond. It's only got 1 valence electron. Carbon is going to tend to form 4 bonds. Nitrogen is going to form 3 bonds. Boron is going to form 3 bonds. Okay? Now the really cool thing is the Lewis dot diagrams were actually devised prior to our understanding of the quantum atom. It just turned out that we talked about the way that things bond, and this worked. And it fits what we know about valence electrons. So kind of a cool coming together of things that happened before the understanding of the quantum atom and things that happen after the understanding of the quantum atom. Does this make sense? So here we have the periodic table, and we've got all of the different families here with their number of valence electrons represented in Lewis dot structure. Now, what do we say? Things that are in the same family behave similarly. Why? No, not the atomic radius. Caitlin? Or Emily! Ah, I still do that. Why? It's the electron configuration. It's the outer electrons. The electrons that the world sees are all the same. So boron, aluminum, gallium, indium, thulium, they all have the same electron configuration. Now notice there is something remarkably absent from this picture. What is it? The transition metals are absent. Why do you think that is? Because those are weird. That's exactly correct. They do strange things. Okay? They're not as predictable as our main group elements. The main group elements are very, very predictable. And that's why we look at the main group elements. Okay? So we don't really have to know anything about the transition metal portion here having to do with valence electrons, or, I mean, we can pick out the valence electrons, but we don't have to know how to draw a Lewis dot structure for these things, okay? They're not very simple. The reason for that is the D's. These are d orbitals. The d block. Notice what else is missing? The f block. Okay? They get to be a little strange. Okay? So, if you look at the group number, remember the A number, it tells you the number of valence electrons, it tells you the number of dots. And if you look at it, it also informs you as to the number of bonds. Remember? So there are 3 open spots, you can form 3 bonds. There are 4 open spots, you can form 4 bonds. So on and so forth. 7A, there's only 1 open spot. You can only form how many bonds? 1. What about neon, argon, krypton, xenon, and radon? How many open spots do they have? None. Do they form compounds? No. Okay? All right. So now that we got the Lewis dot structures, let's talk about bonding. Okay? First off, let's deal with the easiest to do, the metallic bond. Okay? When we deal with the metallic bond, what we talk about is known as the sea of electron model. Okay? And basically, the idea is each of these white spheres represents a metallic atom or a nucleus. Okay? The nucleus. And each of these red spheres represents electrons. Okay? Now, since I drew this, it's not very pretty. Okay? And there's not a lot of electrons. There's supposed to be a lot more electrons. So that it's kind of like these nuclei are just swimming in a sea of electrons. Okay? And this explains the properties of metals very well. Their conductivity. Metals are conductive to what? 2 things. Heat and electricity. They're good conductors of heat and electricity. Let's deal with the electricity first. Well, if these electrons are just hanging out and they're not specifically in any, circling any nucleus, they're just all hanging around in like this, in a sea, then you can push them off pretty easily. And the flow of charge, the flow of electrons is electricity, right? Now what about thermal conductivity? Why does this explain thermal conductivity? Go ahead. You got an idea?
I'm trying to think of what the answer would be.
Okay. I'll give you a clue. Take a look at the spacing between the nuclei, or between the atoms.
They're pretty close.
They're pretty close.
Wouldn't that make heat transfer more quickly?
Why?
Proximity, less distance to have to wait.
Well, what is heat?
When the atoms move and bump into each other.
When the atoms move and bump into each other. So if the atoms are close together,
They can bump into each other more often.
they can bump into each other more often. Does that make sense? All right. It also explains the shine. Because if I have a light wave coming and hitting the surface of this, so light, it's hitting those surface electrons and interacting with those surface electrons. That interaction of those surface electrons allows the light to be reflected. And we see, ooh, shiny. Okay? So the The light comes, hits the surface electron, and bounces off of the surface electron, and you get the reflected light. Does that make sense? Okay, that's probably the most hand-wavy portion of this that I do. Okay, then finally, malleability and ductility. Remember, what is malleability? What is it? When you hit it, right? Malleable sounds like mallet. So when you hit it, what happens to a piece of metal?
It changes shape.
It changes shape. It spreads out, right? What about ductility? What is ductility? If you stretch it, remember it sounds like duct, right? If you think of a duct as being a long stretch of material, when you pull on it, you can form wires. Why does this model explain malleability and ductility? Somebody that I haven't heard from today. I do have all day, by the way.
Would it be because their formation is pretty much uniform?
Okay, explain.
I can't.
Okay. I'll give you another hint. Okay? Imagine putting your hand into a bag of marbles. When you put your hand into a bag of marbles, or packing peanuts, like if you get something that's been shipped to you and it's got packing peanuts, you know those annoying little styrofoam pieces that go everywhere? When you put your hand into it, what happens?
You displace them?
You displace the packing peanuts. But do they go scattering all over the place, or do they stay in the box?
In the box.
Hopefully in the box, unless you start ripping stuff out and being all crazy about it. So when you hit it, what happens? They spread out because they're close together. Now, with the packing peanuts, they spread out only a certain amount because they have a box that's containing them. But with a metal, there's no box containing the metal, but there is the bond holding the metal atoms together. That's kind of like a box that can change shape, so that when you press down on it, they spread out. That's malleability. Same thing with ductility. If you pull on it, they get smaller and smaller and smaller until you end up breaking it, right? Does that make sense?
No,
Okay.
it actually doesn't. So you're saying when you pull on it, it just allows it to come apart because the electrons are.
It's that the metal atoms start to slip past each other until you finally get just a single strand of metal atoms, and then if you can pull that apart even more, you break the bond holding them together.
Okay.
Think about silly putty. You ever played with silly putty? When you stretch it out slowly, it turns into a really thin wire, right? A thin line. And then eventually, it'll break, right? Because the interaction between the silly putty molecules is broken. Okay? Does that make sense?
Since the electrons don't go to any particular atom, they can stretch however they want to without breaking bonds.
It's not so much that the electrons are doing it, but the idea is that the bond, that the sea of electrons in there is holding these atoms together. So yeah, in a sense, it's that you can stretch it out pretty far before it collapses.
Communal bond.
Yeah, it sort of is. It's kind of like a communal bond. It's that the electrons are not shared by any, they're not attached to any one particular thing, that they can go anywhere they want. Yeah. All right, now the ionic bond. Remember, this is the bond between ions. So positive to negative, right? Not negative to negative or positive to positive. All right, so how do we make an ion? We have to remove electrons, or we have to add electrons. If we remove electrons, what type of ion do we make? Not a trick question. Remove a negative charge, what are you left with? A cation, positive charge. Okay? If you're not remembering this up to this point, then you are going to have a real problem with the final. Okay? If you add negative charge, adding electrons results in an anion. Okay? Now, cations are attracted to anions. Opposites attract, right? That's just like the old Paula Abdul song. Okay? Opposites attract. If you've never heard the song, you really should. It's from like 1987-ish. I know it's, ancient history, but it was the first video that MTV played where there was an animated cat dancing with a live-action person. Anyway, what holds these ions together is what we call an electrostatic attraction. The opposite charges attract each other, okay? And the strength of that interaction is given by this equation. The energy of the electrostatic interaction is equal to the charge, Q1, times the charge, Q2, over the radius times kappa. Now, what does this mean, though? So Q's are charges. R is radius, or distance. And that is a constant, what we call the permissivity of a vacuum constant. Now, do you have to be able to calculate this? No. But look at the equation. This equation tells you something. The energy of the electrostatic interaction. What happens to it if the charge increases? So if Q goes up, what happens to E? So if Q goes up, what happens to E? It goes up. Because they're directly proportional, right? If R goes down, the distance between my ions, what happens to E? Does it go down?
No,
What does it do?
goes up because you have less.
It goes up. Because they're inversely proportional, right? If you're stuck as to how this works, just throw numbers in. Let's pretend the top is 1. That's an easy number, right? Start with the bottom being 1. 1 over 1 is 1, right? If the radius goes down, 1 divided by 0.1, is that bigger or smaller than 1? Or you could look at it this way. If the top is 1 and the bottom is 1, you have 1. If the top is 1 and the bottom is 2, is that bigger or smaller? So Q1, Q2 over R is equal to E. I'm not going to worry about my constant at this point, okay? If the top is 1 and the bottom is 1, then E equals 1, right? If the top stays 1, so Q1, Q2 Q, there we go, over R is equal to E. If the top is still 1 and the bottom goes to 2, E is equal to what? 0.5, right? 1/2. What happened? As R increased,
E decrease.
E decreased. Okay? So if you're ever stuck and you get a question like this, where if you don't remember that if it's a dividing, it's an inverse relationship, or if it's directly proportional, that it's going to be on the top. If you don't remember that, plug in imaginary numbers. Not imaginary as in I, but just fake numbers. Okay? And see what happens to the values. Make sense? So that's the problem with dealing with these recordings, is sometimes you screw stuff up, and I can't erase that. So we'll just, and there we go. So this Q1, Q2 over R times the kappa is equal to the E electrostatic. This has a special name. We call this the lattice energy. Okay? The lattice energy is the energy of that bond. Okay? It's the interaction between the negative and the positive ion. Okay? It explains energetically why ionic bonding is pretty favorable. Okay? Does that make sense? Okay. So the higher the lattice energy, the stronger the bond. Okay? And how do you get a stronger lattice energy? What would make E really big? If R is really small and Q is really big. So let's put that into practice. So sodium chloride versus sodium fluoride. What's the charge on the sodium ion? +1. What's the charge on the chloride ion? -1. What's the charge on the sodium ion here? +1 in the fluoride ion? -1. Now, which is stronger? They have the same Qs, right? The same charges. Which one is going to be stronger? Sodium fluoride. Why? Yeah, what did we learn in the last chapter? That radius decreases as you go across, and it increases as you go down. So fluorine is smaller than chlorine. So the energy of the electrostatic should be higher for sodium fluoride than it is for sodium chloride. Make sense? How cool is that? So what if we have magnesium chloride versus strontium chloride? Which is going to be bigger? Or not bigger, but which is going to be higher? Which has a higher E value? Magnesium or strontium? Okay, here's strontium. Why are you saying strontium? Strontium is lower than magnesium, so what does that mean? So the bigger the radius, what happens to E? Right. So you're thinking it in reverse. The bigger the radius, the smaller, because it's an inverse relationship. So that means that magnesium chloride is going to have a higher energy of electrostatic interaction. Now what about something like sodium chloride versus aluminum nitride? which is going to have a stronger electrostatic attraction? Aluminum nitride. Why do you say that? Right, so nitride is higher on the periodic table, which means it's going to be bigger or smaller?
Or small.
Smaller, right. But that's not the only thing. What's the main reason? What's the charge on the sodium? Sodium is a +1, right? What's the charge on the chlorine? -1. What about on the aluminum? +3, and then the nitride? -3. Look at that, the charge. Much bigger charge. The bigger the charge, the bigger the energy of the electrostatic interaction. Make sense? All right, so we can take a look at ionic bonding in terms of Lewis symbols. So here I have lithium fluoride. Lithium has one valence electron. It's in the 2s orbital, right? Fluorine has 7 valence electrons in the 2s and the 2p orbitals. Now, if lithium gives that electron to fluorine, then lithium has a positive charge and the fluorine has a minus charge. And look at what they've achieved. They've achieved noble gas electron configurations, right? So really what happens is this happens in a couple of different steps. The lithium ion, or the lithium atom, gives off its electron to form the lithium cation. That electron then attaches to the fluorine to become the anion. And then the cation and anion see each other and form the ionic compound, lithium fluoride. Okay? So notice how these are drawn. These are actually drawn slightly incorrectly. If we're doing Lewis dot structures for ionic compounds, we should really have it written as such. Lithium with the cation, and then we place the fluorine in brackets and give it the anion charge. And make sure that you put your dots all around. So that is the more correct way to write that structure. Okay? Does this make sense? Anybody having problems? All right. So, as I talked about the energies of these ionic bonds, as Q goes up, energy goes up. As radius goes up, energy goes down. Inversely proportional. And we did these, and we saw that the smaller you are, the better off you are. And the more charge you have, the better off you are. In terms of energies, the stronger your bond. Okay? Now, this can be looked at in terms of what we call a Born-Haber cycle. Okay? This is nothing more. Oh, look. Delta H is equal to H1 plus H2 plus H3. What do we call that? Addition? Yeah, it is addition. What does this kind of look like?
Some dude's law that says if you go through the steps in a reaction, it's the same.
Right, it's that some dude's law that says that a reaction can be thought of as a series of steps, right? Who was that dude? You don't know?
No.
Well, let's put it this way. There's a reason that enthalpy has the letter H. Hess's law. This is Hess's law. So, Hess's law states that a reaction can be thought of as a series of steps. Let's take a look here. So, lithium solid plus 1/2 fluorine gas turns into lithium fluoride. That's an enthalpy of formation, right? Delta H overall, that's the enthalpy of formation. First step is you have to sublime the lithium. Because when we talk about lithium losing an electron to become the lithium cation, the energy we talk about is the ionization energy. Ionization energy is the energy required to remove an electron from a gaseous atom or ion. So it has to be a gas first. So first we do the sublimation, then we do the ionization. Okay? Now, fluorine is already a gas, but it's a diatomic, right? I only want one fluorine, right? If we take a look, when we had our drawing, we had lithium dot plus fluorine with 7 dots, right? This was an F2, so I have to break that apart. So that's the energy of dissociation. Breaking that covalent bond into 2 fluorines with 7 electrons each. Then when the fluorine gains an electron, that is the electron affinity. And remember, the electron affinity should be a negative number. Your book, for some reason, likes to pretend that the electron affinity should be a positive number, but in fact it's a negative number. You get energy back when you add an electron to an atom. Okay? Particularly things like oxygen, fluorine, all of our nonmetals, it's actually very exothermic to get an electron. Okay? Now, if that were the only thing, then it would just be the sum of those, but we know that that's not the case. We also have to deal with the lattice energy. And then the lattice energy added in gives me my overall reaction. Does this make sense?
Yes.
So it's just Hess's law. But you have to know what each step means. Why do we have to sublime? Why do we have to ionize? Why do we have to dissociate? Why do we have to have the electron affinity? And why do we have to have the lattice energy? If you don't have that lattice energy component, which is negative 1017, and the overall here is negative 594, that means if I didn't have that lattice energy component, the reaction would appear to be endothermic, but it is very, very exothermic. So the lattice energy has to be included. Okay? Does that make sense? Do you think you can replicate a diagram like this?
We have the energies.
If you have the energies, you should be able to, right? Because you have to think about what does each energy mean? Ionization energy, energy of sublimation, dissociation, electron affinity. Okay? Does this make sense? All right, now covalent bonding. Covalent bonding occurs when we have a sharing of electrons. Now this sharing can either be equal or unequal. Okay? Kind of like any relationship you've ever been in. Whenever you share something with someone, it could be equal sharing or unequal sharing. Now how do covalent bonds form? This is different than an ionic bond. An ionic bond, the math is easy. That electrostatic energy, E electrostatic is Q1, Q2 over R. Beautiful, nice, simple, easy. This is not so easy. This occurs from atomic orbital overlap. Okay? That overlap of these orbitals, or overlapping space in which electrons can be found, accounts for our sharing. Now, the distance between the atoms is pretty specific, okay, what we call a bond length or bonding distance. Such that if you go too far or too close together, the energy is not favorable, okay? If you go too far apart, then you don't have a bond, okay? So there are specific bonding distances that give us the optimal length for a bond to occur, okay? Now we can share multiple pairs. So we can have 1 pair, 2 pair, or 3 pairs of electrons. These result in what we call a single, double, or triple bond. Okay? Does this make sense? Yeah.
Is it possible for an atom to be covalently and ionically bonded?
Yes. It is possible for a covalent and ionic bond to exist within the same compound. So, for example, lithium nitrate. The lithium is a cation, the nitrate is the anion, but nitrogen to oxygen is covalently bonded. And then it is ionically bonded to the lithium. Okay? So, the bond length here tells us a couple of things. Number one, 1/2 of this bond length gives me my atomic radius, right? That's how we measured atomic radius. So 1/2 the bond length gives me my atomic radius. But it also tells me a couple of other things. It tells me about the strength of the interaction, how strongly these things are going to be attracted to each other. Okay? So, for example, hydrogen to hydrogen, close together. Hydrogen to iodine, farther apart. Okay? In other words, that hydrogen is not necessarily going to be very closely attached to that iodine. Okay? Now, is it a perfect thing? It's not like Q1, Q2, and R. Okay? There are exceptions. But in general, we can say this, that a triple bond is going to be shorter than a double bond, which is going to be shorter than a single bond, and that a triple bond is going to be stronger than a double bond and is going to be stronger than a single bond. Okay? Does this make sense? Yes? No? So, I'm going to ask a question. How do they measure that? Is there some little dude with a ruler going, yep, 74 picometers. From the nucleus to the nucleus. But how do they do it? A really good microscope. No equation.
Oh, just take a crap ton of them and measure them that way.
Okay, if you take a crap ton of them and measure them that way, how are you going to measure them? How?
Dividing it by how many atoms you got.
But how do you make the measurement? That's what I'm trying to get at. How do you make that measurement? The way we make these measurements is that we make the molecule interact with light. And we do take a crap ton of these measurements and then average the measurements. This gives us an average bonding distance, which gives us an average atomic radius. Okay? These numbers are not absolutes. They're not something you need to memorize. Okay? You need to know the trend. Triple, shorter than double, shorter than single. But it is kind of interesting to see how they make these measurements. Basically, what you do is you've got your atoms, your nuclei, they're attached by the bond, which acts like a spring. Because we know that atoms are constantly moving around, right? If we find the right frequency of energy that make them bounce like a spring, we can use what we know about springs, what's known as Hooke's law, to actually calculate the distance between the atoms. Sort of, yeah. Now, the thing is, if we take a look at distance versus energy, and there's a 0, if you're really, really far away, so two atoms really, really far away, are they really bonded? No, so the energy of the bond should be 0, right? So now as they get closer and closer together, we start to get a little bit of overlap. So what we get is an energy dip. And then if we start trying to jam them closer and closer and closer together, then our internuclear repulsions start to take over and the energy goes way high. Okay? So that energy goes way high, which is a problem. Why do I say that's a problem? Well, what is one of the big issues that we've had over the past couple of presidencies? There's one big issue, not the war, okay? You might notice it when you go to the gas station. Cost of energy, right? Energy is really expensive. Gasoline this morning was $3.79 a gallon near my house. I remember when it was under $1. It used to be 79 cents. I could put $5 worth of gas in my car and drive for nearly a month. I didn't go very far, but still, $5 and drive for a long time. So we're looking to new and better energy sources. And one of the energy sources that we've been trying to do for the past 35 years or so is what is known as nuclear fusion. Why is nuclear fusion such a good thing? Well, that's what powers our sun. I don't know if you've noticed, but there's a lot of energy that comes from the sun. Okay? So if we can take two helium nuclei and get them really, really close together, such that the nuclei touch, energy is released, and a lot of it, because it becomes helium, which is very stable. But take a look at what happens to the energy as you get them closer and closer together. It takes a lot of energy to push those two atoms together. And unfortunately, it takes too much energy. The amount of energy we put in is not compensated by the amount of energy we get out. In other words, it still takes energy to make fusion happen. Now, we have gotten closer, much, much, much closer in the past few months. They're almost at the break-even point. Once they can get past that break-even point and maybe make it a little bit more energetically favorable, perhaps we can have only a handful of electricity generators. How nice would that be? We wouldn't have the greenhouse gas emissions. Coal plants, which are actually the most efficient at this point, would be cut out. We wouldn't need them. And it all has to do with dealing with this bonding length. Yeah, Christina.
I was wondering about that energy fusion thing they're talking about. Isn't that with the tubes or something like that? Something you use with tubes? Maybe I'm thinking of something different, but I thought it was somehow they use these tubes and to dispose of them, they said it would take thousands of years to dispose of them.
That is fission energy. That's the nuclear power we have now. Okay? The difference between the nuclear power we have now and the nuclear power of the future, fusion, is that the nuclear power now gives off things that are radioactive. Fusion would give off helium, which the funny part about helium is the only way we find it in nature comes from radioactive decay of uranium. Now, Byron Nuclear Power Plant is a fission power plant. They are actually very, very energetically favorable. Okay? You can get a good amount of energy coming from a nuclear power plant, but people are scared of radioactivity. And the disposal of radioactive waste is a problem for some people. Okay? There's a lot of different literature out there against radioactive nuclear power plants and for nuclear power plants. I personally am for them. Okay? Because of their efficiency. But a lot of people just don't like that whole worrying about radioactivity. Yeah.
What kind of waste do they put out?
The waste that they put out, what is it? It's uranium goes to something. I don't remember, in all honesty. There's a radioactive decay cycle that what they do as things decay down, they become different elements. But I don't recall what it is that they specifically kick out. It's probably a mixture of radioactive isotopes. No, they don't stay in the same group because as you're giving off radioactive decay, the alpha particle means you'd lose 2 protons, so uranium would lose 2 protons to become thorium. Okay? And then if thorium were to lose 2 protons, it would become what? 90 minus 2 is?
82.
90 minus 2? 88. 88 is radium. Okay? Now there are other types of radioactive decay. Okay? So it's probably a mixture of stuff. I'm not really sure which one. I think thorium is one of the major components, but don't quote me on that. Now you're going to make me go and look it up because now I'm going to want to know. Okay? But the point is yes, it does take thousands of years for it to become a more stable isotope that's non-radioactive. It's just the nature of physics. Yeah, if they bury it in cement and then they put it underground and then hope that there are no earthquakes and stuff like that. And there's, like I said, there's a lot of literature for and a lot of literature against. Actually,